In this video, we're going to introduce the idea of an inner product and also the idea of an inner product space. Now, the easiest way for me to introduce this idea is to paint an analogy with the Euclidean vector space and the dot product. So our vectors in Rn, we have a pretty simple way of multiplying them, if you will, right? And that process produces a number, right? So if I give you any, let's say, a pair of vectors in R3, you can compute the dot product and then the end result will be a number. Well, what we want to be able to do is to generalize that for all vector spaces and maybe just come up with more general ways of thinking of the dot product. But we don't want to use the word dot product because that's so like well-known, very specific process. So the generalization of the dot product is an inner product, right? And let's just maybe do kind of a parallel to see where we are, right? So in Rn, we have our dot product, which we usually denote like this. And as far as the formula, I'm not going to write down the formula, but we know that when we compute the dot product, this produces a real number, right? Now let's think of some other types of vector spaces that we know. In fact, and I'm going to throw Rn in there because what we're going to do today can actually extend what we think of our regular dot product as long as certain properties are upheld. So let me put Rn, but what about like the space of matrices? So like our M and N like that, or our space of polynomials of a certain degree, like Pn. And then even the space, just as an example of continuous functions, let's say over the entire real line. Is there a way for us to define a process where we take a pair of each of these types of vectors, we combine them somehow and produce a real number? So the notation that we're going to use for an inner product is not a little dot, but it's going to be angle brackets. And I know if you've done other work in areas where you use angled brackets to denote a vector, well, that's not what we're doing here. So the way we would indicate the inner product of u and v, whatever those vectors are, we would put the two vectors separated by a comma there in between these pair of angled brackets. But whatever happens is, whatever that process looks like, we still want the end result to be a real number. Because what that will then allow us to do is to take the idea of an inner product and talk about distance and length and orthogonality in all these different vector spaces, which is like so crazy cool, all right? But before we get to that point, we have to kind of lay the groundwork. So what do we require of this? Well, again, let's maybe do the analogy. Let's see what we know, some of the properties that the dot product has, right? So over here, we're just a regular dot product. Let's write down what we know about the dot product. So we know that u dot v is the same as v dot u. All you got to do is just look at the algebraic definition of the dot product, and it makes sense, right? Because we're working with addition of real numbers, basically. Right, so that's one. And let's look at another one. So this is the commutativity property. We also have a distributive property that says u dot and then the quantity v plus w. You can distribute that dot product across that sum, so it becomes u dot v plus u dot w, right? So that's an important property. There's a property that involves scalar multiplication that basically says if you scale a vector and then take that scaled vector and then do a dot product with another vector, the result will be the same as if you do the dot product first and then you just multiply the result, which is a number, by the scalar c, right? So you got that. And then we also have that if we take the dot product of a vector with itself, we know that we can't get something negative. So that's got to be greater than or equal to 0. The only way, and I'll write this kind of as a a subsidiary of this property is that the only way v dot v is equal to 0 is if the vector itself is the 0 vector, right? So yeah, so those are some of the properties that we have for the dot product, and we've used several of these previously. But now let's translate those to what it would look like with our new notation and the idea of an inner product. And while we write this down, let me just say that it's not always easy to go through and verify that, because remember, these properties are super general. These are saying for every vectors u, v, and w, and every scalar, then these things have to be true. But again, let's state the axioms of an inner product. So basically, wherever there's a dot, we're just going to replace it with our new angled bracket comma notation. So the first one is that the inner product of u and v must be the same as the inner product of v and u. Right, so that's got to be a given. The distributive property, you just have to be careful how you write that down. Remember, wherever the dot is, that's kind of where the comma is going to be, and then we have to put angled brackets around the separated pairs of vectors. So the left-hand side of property 2 is saying that the inner product of u with, when I say with, then there's the comma, v plus w is the same as the inner product of u and v plus the inner product of u and w. Yep, so kind of split it apart. That's the distributive property. Then you got the scalar property. This one's a little bit easier, but c times u, the inner product of c times u and v, yeah, you basically can factor out the c, whatever is being used to scale your vector here, that can go outside the inner product. So find the inner product first, and then multiply that by c. And then the last one is basically saying that the inner product of a vector and itself is always non-negative, right? And the only way, right, the inner product should come out of a vector with itself should come out to be 0 is if and only if that vector is the 0 vector, right? So in general, it's hard to go through and verify. Sometimes it's really not that difficult. Other times, yeah, you have to take some work. But this is what we would require of an inner product, right? Just to make sure that we get all these nice algebraic properties. All right. So when we have yeah, so this thing, right, that we're denoting this way, obviously this is our inner product, right? And if we now say that we have a vector space, a general vector space, along with an inner product, I'm just going to leave it kind of blank right there. So these two things together form an inner product space. All right. Okay, so you might be wondering, like, what would these inner products look like? So let's just do a few, relatively quick examples. And what I'll do is I'll illustrate it that we can first generalize the dot product, make it more than just what we know of the dot product, and then also look at some examples for matrices and for polynomials. All right. So yeah, so let's just look at a couple of examples here. And in my first example, let's say my vector space is R2, right? So very familiar vector space. And I'm going to define the inner product like this. I'm going to say the inner product of u and v is going to be u1, v1. Well, that looks familiar. But instead of just taking plus u2, v2, I'm going to take 2 times u2, v2, right? Inner products that look like this, these are referred to as weighted. You could say this is a weighted dot product, right? So weighted dot product, essentially, right? And your regular dot product is sometimes referred to as the Euclidean inner product, but anything, yeah. So this very very similar. So if let's say my u, and I'll write this as a column, doesn't really matter. Let's say 2, 3, and then let's say v is 1, -1, then the inner product of u and v using our weighted thing, it would be 2 times 1, right? So that's u1 times v1, but then I have to take plus 2 times 3 times -1. And then this will give us 2, and then this is -6, so then this will be -4. And there you go, right? Now, again, I didn't go through and verify if this is formally an inner product, but yeah, this idea of a weighted dot product is actually very important in lots of modern applications, right? Where you might want to put a greater weight on one of the terms that make up your dot product as opposed to having it all equally weighted, right? Which is what your regular dot product would do. Yep, so there's one way to kind of extend it. Let's look at a second example. Let's say our vector space now would be 2 by 2 matrices, right? Let's say 2 by 2 matrices. So we got our M2, 2. And so here's what I'm gonna say. This one's gonna seem pretty trivial. I'm just using A and B because that's how we usually represent matrices. So if I want to take any pair of 2 by 2 matrices and combine them, a natural way to do it is, because matrices and Euclidean vectors are very similar in their even the way we denote them, right? I'm going to take A11 times B11 and then plus A12 times B12 and then plus A21 B21 and then plus A22 B22. I might say, wait, that just looks like, it looks like a dot product where you're just multiplying corresponding entries or components or pairs. And yeah, this is an easy way to work with matrices. Just pretend that they're vectors, right? Well, you don't have to pretend they are, but in terms of how we define the inner product, just take a leaf from what we've done for Rn and then just translate it over here. So again, just a quick example. Let's say A is 4, 1, 7, -3. And then just for kicks, let's take B to be our identity matrix, just for fun. So there is B. So then the inner product using this definition of A and B, so it's going to be, I'll write out the products and then the sum. So you'll have 4 times 1 and then plus 1 times 0 and then plus 7 times 0 and then plus -3 times 1, so that's going to give us 4 minus 3, so we have an inner product of 1, right? Pretty straightforward. Let's move. Now, there are other things that you can do, right? But the whole idea of these operations that we're defining, and if we're doing it more formally, we have to verify that all those axioms hold. The end result of all our computations must be a real number, right? It's got to get it. In order for us to do more with this stuff, we need to get a single number out of this. Let's end with a look in our polynomial space. So what if our P, let's say it's something like P2. Let's keep it pretty simple. So remember what P2 represents? It's the set of all polynomials of degree less than or equal to 2. And here's how, so I'm just gonna use F and G because these are gonna be polynomials. So the way we would combine these two, let's do some calculus just for fun. Let's say what we would do is we would integrate from 0 to 1. Now, because the end result has to be a number, I couldn't do like an indefinite integral. I would have to do a definite integral, so I end up getting a number. And let's just say we just do F times G, right? So that's our inner product. Now, again, you might say, does this really have the properties that we want? Well, if you think deeply about some of those things in calculus, then yeah, you'd realize it actually does have the properties that I want. So as an example, let's say f of x, I'll keep it pretty simple. Let's say one of them is just x, and then let's say g of x is something like 2x squared plus 1. So if I wanted to find the inner product of these two vectors in P2, right? So this is how we would write it up, f in comma g in our square brackets. So it's going to be the definite integral from 0 to 1, and I would just multiply these two. So it'll be x times the quantity 2x squared plus 1. Obviously, if we remember, our process of integrating is, yeah, we can't take the antiderivative of the terms separately, so we have to distribute. So we'll have 2x cubed and then plus x. Then we find our antiderivative, which is going to be 2 over 4, x to the fourth. So that's going to be 1 half x to the fourth, and then plus 1 half x squared. And then we use our wonderful FTC. So we're going to end up with, looks like 1 half plus 1 half minus 0, and we get a value of 1, which is really interesting, right? Which is really interesting because if you look at these two examples, the second example, it was matrices, and we just kind of did what would be a natural extension of the dot product, and we come up with an inner product of 1. And then down here, very, very different set of objects. It's now polynomials, and now we're using an integral, definite integral, and we still come up with an inner product of 1. And then what we're going to do in subsequent videos is we're going to say, okay, once we have a handle, right, if we accept this idea of an inner product, how does this then translate to things like answering the question, what is the length or magnitude of a vector, or what is the distance between two vectors? And again, we'll just continue this generalization using this new idea of an inner product. So if you're up for the challenge, join me on that journey and join me in the next video. See you then.